We have next Karin Erdmann from Oxford, who will talk about periodicity for finite-dimensional semi-injective algebras.
Thank you very much, and thank you for organising for inviting me and letting me speak here. And yes, right. So this is most of it is joint work. So I'm glad that Osamu has done a lot of background for me and definitions. Anyway, so my field is also algebraically closed for simplicity, and so I have an algebra which is always finite-dimensional plane algebra. And it is self-injective, so self-injective, and or a Frobenius algebra, if you like. And so you have always that A is, as a one-sided module, isomorphic to the dual of A, and D is the same. And yes, right. So yesterday we had lots of twists, and so if you want to view it as a bimodule, then A will be twisted. So you have an automorphism which twists A. Okay, come back to it. And yes, right. So if you have looking at finite-dimensional modules, and you have finite-dimensional module, then it has a projective cover. So P is a projective module, and it's as small as you can make it. And then the kernel is unique up to isomorphism. And it is sometimes called Heller operator or syzygy, or whatever, maybe syzygies. And you can iterate it, so you have omega squared n, omega 3n, and so on. And so if you come back to the starting point, then n is periodic. Right, and yes, right. Should also have said that because dually you have injective. Yes, so I don't want to do that now. But anyway, then you can look at A. It's an A bimodule, and so you can view it as a right A enveloping algebra. A tensor right, A op tensor A module. And so this is usually called enveloping algebra. And then you say that the algebra is periodic. If yes, so if A is periodic as a bimodule, so if A is periodic, so somehow some syzygy is isomorphic to S bimodule. So this is a very good property because if so, then all one-sided modules A modules are periodic. And in fact are period dividing D, right? So period would be the minimal such a. Okay, so that's a very good property, and so one would like to know when this happens. And there is a connection with Calabi-Yau property, as Osamu has told us. So you have the stable category. Triangulated, so this has a suspension. So yes, I haven't said what omega inverse is, but you can also have omega inverse, the kernel inverse of n is the co-kernel of injective Hall. Injective Hall. So you have omega inverse. And so the stable category is triangulated. Which has suspension is omega inverse. And so it has a self-functor. As Osamu defined, and this is factor, which is S, which is, and this has omega converse with mu, and so what is this mu? This appears again here, so mu is tensor with EA, and so you can talk about Calabi-Yau, so it's Calabi-Yau in this sense. So this stable category is Calabi-Yau. Mod A is Calabi-Yau. The Calabi-Yau is omega inverse. Going that. Right, with black dots. Yes, right, it's isomorphic to omega mu, or if you want omega minus b minus 1. So in the special case, when this mu is the identity, that happens as well. So this means that A is symmetric, then of course it's not an algebra. Okay, right. So why does one want to know, I should probably not forget to do this one here. So I'm just going to repeat these things. This is what I had just written down. So define periodic and define what an algebra, when an algebra is periodic. And so then you can define third duality. And then now we'd like to know, why do we want to look at, why are we interested in periodicity? So yes, one thing I should say is we had thought about preprojective algebras just now, and yes, Osamu has actually put them into wider context because he has deep preprojective algebras, and my version is put them into wider context, but I'd like finite-dimensional algebras and just preprojective in wider context. But my context would be of self-injective algebras, right? So I'm not feeling happy about global dimension, so I'd like self-injective algebras. So it's a different context. And of course, then there are some other periodic algebras in the world. So group algebras with so quaternion groups. The group algebras of quaternions have periodic. So if you take G of quaternion group or generalized quaternion, and characteristic of the field equals 2, then this is periodic. So this is fairly classical and could even put this on that venue. And so I would like to do this into wider context. Right. then there is this Calabi-Yau property. So Calabi-Yau is another reason why one would like to know that. This is a nice symmetry. And then Osamu has also defined cluster tilting modules. So cluster tilting and yes, right. So maybe I shouldn't write this down, but so some years ago, Thorsten Holm and I were looking for cluster tilting modules just for whether they occur in nature, right? Because this was a long time before Osamu, well, sometime before Osamu invented D there. Anyway, so we looked at that and then we couldn't find any. So eventually we proved that if you have a self-injective algebras which has a cluster tilting module, then it must be true that all modules have bounded periodic resolutions. And that is a fairly strong property. It holds for finite type, and it holds for preprojective algebras, but otherwise it's not so common anyway. So this is the reason, if you want to find cluster tilting modules, then you must have an algebra where modules have bounded projective resolutions. And well, yes, I mean, so one way to have that would be a periodic algebra. In fact, I should say it's not known whether you can have an algebra where modules have bounded projective resolutions, but which isn't periodic or has any periodicity. So that's one reason why I was interested in that. And then there is the question or conjecture as well. Maybe it's a conjecture, I'm not quite sure. Suppose you have an algebra so that all simple modules are, all A modules are periodic. Is then aperiodic. So we have seen that the converse is holds. So if the algebra is periodic, then all modules are periodic. But this question is, can you have the converse? And in fact, it would be enough to assume that all simple modules are periodic, because by homological algebra, we would get some conclusions on that. Anyway, so some evidence is this theorem by Green, Snusher, Solberg. So you have equivalent conditions. All simples are periodic. And it's the same as knowing that the some syzygy of A as a bimodule is a twisted bimodule, and sigma is some automorphism of A. So this looks rather as if it should be true, because it's almost, I mean, it looks almost if this is true, because if the automorphism is finite order, then A is periodic. So the question really is analyzing these syzygies and decide whether or not you have an automorphism of finite order. And this turns out to be, well, I don't know what is true or not, but there are lots of cases which have been looked at, and classes of algebras where it is true, but I don't know. Anyway, so let me come to the first thing, is generalized periodicity, generalized preprojective algebras. So how am I time? So maybe the Newton Institute is the place in the world with the best blackboards, right? You have them everywhere, right? You have them in the lift as well. Are they still in the lift? Okay, so let me look at generalizing some other preprojective algebras. So my example today is would be something like P of A5. So the quiver would be something like that, 2 pi particle. 5. And I'm afraid my relations would be A bar. Almost have it's called A bar and some of A bars, you know. So yes, right. And I also would say that A double bar is A. Right. So then I can write the relation like that. And of course, my signs are different from last an hour ago, but it doesn't matter because we have a tree, right? Okay, so this is A5, double quiver, you take the double quiver of A5 and you have these relations. Right, and so yes, right, it's known that for these, if A is something like that, then the simple modules of A is I simple. You have the property that omega 3 of Si is isomorphic to the twist of Si by this automorphism. And so this is known and not so hard to show. And so the question is, if you would like to generalize it, then you might look at algebras. Which algebras have which self-injective algebras? Omega 3Si simple for all. Right, and this turns out to be a good property because you can relate it to that, and then you can actually determine the quiver via generalized pattern matrices. And yes, right, okay. So the quiver is, you can define the quiver so I would like to explain where these pattern matrices come from. Right. So yes, as Osamu explains that I can assume that the algebra is basic, and up to Morita equivalence, I can write it as KQ modulo I. Q is the quiver, and KQ is the path algebra, as before. And so then I can also write down the indecomposable projective modules. So I have the paths of length 0, so they are called EI, one for each vertex. And so I can write this one here, indecomposable projective. And the simple modules would then just the simple portions. So this would be Si is EI and modulo radical, EIA. And so then I assume that omega 3 of SI is simple again. So all I, so it will be isomorphic to some other simple, sigma I, and sigma is a permutation of the vertices. Right. So what can I do with that? Well, I have an exact sequence. Start with SI. So then I have a projected cover, which is PI. Yes, right. So there is the omega SI. And I take the radical of this, and so I take a projective cover of that. And yes, what is that? Will be the projectives. This one. So in my quiver I have vertex I, and then I have all arrows starting at I. Yes, right, so there, sorry. And this is, sorry. No, I'm getting confused. So I take, okay, so I take all vertices J, so that there is an arrow from I to J, right? So I have to take this. Right. And so then there is omega squared. And then there's another, which I call dA. And then the next one has to be SI, because I have period S sigma I, because I have period 3. And so what is this G here? And then this PGA must have so-called simple submodule. Is the injective has the injective with simple couple as sigma I, and so you get an automorphism, get a permutation, get an automorphism of the quiver. So if you take this G, you can work out what it is. It's a composite of mu and sigma. And it gives the bijection on arrows. So whenever you have an arrow from I to J here, then you must have an arrow from J to G of A, G of I, and this is A bar. And so this looks as if you could have something similar to preprojective. And then I won't write down what the details are, but you get a Cartan matrix out of that. That's what I just said. And so you look at the orbit of this G on vertices, and you get a generalized Cartan matrix out of it. And Right, and if you have that, then you would know that the quiver has to be related to almost a Dynkin quiver, and so you get these quivers out. So type A and type B, you can get that. Type C, D, E. You can also get type F and type G, and then there is one exception where you actually have a loop, and this is possible here. So you can have a loop, and you can, which is not Dynkin, but you can have that. And so when you have all these quivers, then you can construct algebras. And so, for example, if you take if your graph is type L, you would have graph like that. Then what you would have to do in this case is a quiver. You take a double quiver. However, in this case, you will not double the loop. You just keep the loop. And then you yes, right. One actually I wanted to look at is an interesting one is what is called E3 here. This is type L something or E3. You would have as a quiver you would have this one here. And then you would want to introduce relations, and you can use the automorphism. So you use the automorphism which we had before to get relations, to get A goes to get A bar for each row of A. So in this particular case, if this is A, then this would be A bar. If this is epsilon, maybe then epsilon is equal to epsilon bar. And so if you here have an A, then the A bar would have to be which one? This one. And then you can define an R, and then you get again an algebra which looks like it should be maybe should be pi null. So you get this quiver K2 delta. And you also have then relations which look like mesh relations, which are mesh relations. So this is always self-injective, and when you have Dynkin ADE, you just recover the preprojective algebra, but in general you get some new algebras. And I like this one here because you can see how these things might be related. So the on the right, I've drawn the preprojective algebra A5. The quiver of that. Sorry, I'm underlining. Okay, so this has a universal cover here because you can. Okay, so you can take this quiver here and just repeat. I mean, just extend it to both directions, and you have commutativity relations. So from 1 to 3 to 1 is the same as from 1 to 0 to 1. And everywhere you have commutativity relations. And then you also have, at the end, you have from 3 to 1 to 3. Well, there is nothing here on this side, so it has to be 0. So you have these so-called mesh relations. And so if you factor this out here by the automorphism, which is just the shift one up, then you get the preprojective algebra. So now if you change the automorphism a little bit, instead of the shift, you take an automorphism, so phi was the shift. And this rho is the reflection in the central line. But if you compose this shift here with reflection, so what happens here? You shift up by one, and then you go to the right. You get some diagonal automorphism. So you go zigzag all the time. Yes, we have some zigzag algebras later. And then you get the new algebra, which is this type B3 algebra. And so this is, then you can in fact use this to show periodicity as well. Right. So what else did I want to say about that? Yes, right. So you can get more algebras out of it. So you have a universal cover. You can get also new algebras. You can get larger algebras. You can also get n-fold extensions. And you can also get deformations at branch vertices or at special vertices, at some vertices, special vertices. For example, if you have type D, then you can deform a branch vertex and you get classes of algebras. And I don't really want to go into details here, so this would be the m-fold extension with that. And then you can deform relations and get new classes of algebras in both, and then you get more algebras, and of course all these actually work out, come naturally if you want to classify algebras where omega 3 of a simple is simple, and you get a complete list here. And what isn't clear is which of these algebras are periodic, and for the n equals 1 it's okay, and no okay. Yeah, what's open is if you take the deformations, whether they're periodic or not. And so this is actually rather messy, and so if the f if the identity is yes, 1, then algebras are periodic. And there's a lot of work which Douglas, which he has a nice method, which I'm not going into, but in general it's not clear. Right. So yes, right. The I shall now discuss the periodicity question or conjecture. So we had this earlier. So the question is if all simple modules are periodic. Does this imply that A is periodic? So in most of the examples in nature, this has been established. So for example, you can look for blocks of group algebras, and then you look at finite type. So if an algebra has finite type, then trivially all simple modules are periodic. But it's not clear whether algebras are periodic. So there have been several papers on various cases, but then Alex Dugas has a general proof. So basically he uses a new idea. He shows that periodicity is preserved if you do finite Galois suitable finite Galois covariance. And so then the question is, how can you use this method more generally? And so with Andrew Skromsky and Jarzbierkowski, we have generalized this to polynomial growth, tame with polynomial growth. Then if all simple modules are periodic, then A is periodic. And yes, right. So what is tame with polynomial growth? So tame would be basically, roughly speaking, you can classify the indecomposable representations. So this means if you want to make this formal, then for any dimension D, the indecomposable modules of dimension D I should say almost all indecomposable come in one parameter family in finitely many one parameter families. And polynomial growth means that the number of these families there's an n so that the number of families for dimension D is bounded by e to the n. So the number of families on board dimension. And I suppose the example of if you take the smallest algebra k x y x squared y squared, this is tame, and so this is tame. And indecomposable, and this is for each even dimension, odd dimension. There are only two indecomposables, and for every even dimension, there is a one parameter family, just one parameter family. This is sort of classical, and it's known as Kronecker pencil of matrices or something like that. And so if you only have one parameter family, then it will even be of polynomial growth. And so it is it's polynomial growth because it's actually constant. And just take this or of course, yeah. Right. But if you take kxy x squared y squared, and you take xy to the k minus yx to the k. Sorry, I forgot the non-relation, right? No, and so the non-commutative ones, if you have k greater than 2, this is tame, but it's not polynomial growth. Because you can parameterize indecomposables by worlds, suitable worlds in x and y, and they grow fast. Okay, right. And so for tame polynomial growth, it's possible to say to show that show periodicity. So if you have an algebra of tame polynomial growth and all symbols are periodic, then the algebra is periodic. And we also have a complete description of these algebras. I should say something about that, and I can do that. Yes, right. So about and probably just turn the page. Yes, right. So in general, if one would know that if A is, so A can be either standard or non-standard. Then it will be of the form B hat G. So this will be some Galois covering some repetitive algebra. I probably shouldn't go into details algebra. And it's similar to the picture I had before. So yes, right. So here this would be a typical picture what you do. So this think of this mesh algebra, then you have a covering and you factor out by some suitable group of automorphisms, so it should be admissible in some appropriate way. Suitable. And then and in this case you can actually say, because if you have polynomial growth, then this B has to be and periodic. You can show that this B has to be something that's called tubular in the sense of classification. And well, yes, I mean this comes because it's derived equivalent to coherent sheaves on some weighted projective line, and this comes from that. And then you would have to show it's periodic. Question is periodic. So you can use derived equivalence and use derived equivalence and finite coverings. This is the Dugas idea, and we use for few cases. Algebras. And then the non-standard ones, the non-standard are then Sokal deformations of these, or deformations of these, Sokal deformations of these. So you just change Sokal scalars. And then do these things by hand. Right. So you have 5 families of algebras, and so for each of them you would just compute the first 2 steps of a bimodule isolation. So I think the longest one we needed to do was length 8. So this is about. Right, okay. So then question is what you do if you don't have polynomial growth. Well, this is well, if you don't have tame, I think this will be quite difficult to do with methods of this kind. And not polynomial growth, maybe there aren't any difference. Tame, not polynomial growth. Right, and so then this brings me to the last part. So generalizing quaternions. So we would like to put quaternions into wider context. So we call A is a generalized quaternion type. Which is, yes, it should be symmetric. A is same, the same I explained just before. Symmetric, so this mu is the identity. Mu is identity. And all simple modules. Period, omega period form. And yes, right. So an example would be the group algebras, the quaternion group. These quaternion groups are generalized quaternion and characteristic is 2. Or also a block of the group algebra with quaternion defect group. Defect group quaternion. There's pseudo two touches quaternion. So for these things here, I mean, it's much more special in these cases here. The Cartan matrix of the algebra is non-singular, and so this is a very strong condition. And so previously we haven't really tried to deal with this in general, but now we can do that. And so we have some better understanding and recovered from that. And so you can view this in the context of surface algebras. So I should be introducing matrix surface algebras. Okay, so the algebra should be of the form A equals K2 modulo I. And so I'm looking at Q, and I define triangulation trigger. So it should be 2 regular. So what is that? So it means that for each vertex, we should have 2 arrows in and 2 arrows out. Precisely 2 arrows in and 2 arrows out. And then it should have a permutation of the arrows. F of the arrows, and F3 should be the identity. And because this terminating point of alpha should be the starting point of F alpha. So I should be able to compose these two things. And so what you can construct these So these two correspond to, in some sense, triangulations of surfaces. And you allow boundary components and self-folded triangles, and of course basically what happens if you have a triangle, then you would of course take a quiver like that, or of course you could change the orientation in any given triangle if you like. And if you have a boundary component, you would just have one loop, and f squared, that's delta, and f of delta is delta. You can do that as well. Delta. And I've drawn a few examples. So my favorite examples here. So the top one is what you get if you take a tetrahedron, and it has a natural orientation. And so if you write down the figure of that, you get a picture like that. And so you have triangles, which I have shaded. So this is F. F goes around this triangle, but then G is coming in a second, and so you have another one here. And I haven't shaded this one here, so this will be one loop, which is formed by F, and this triangle, which I've forgotten to shade. Okay. So then you have another permutation, G. So what is G? Right, so if you have an arrow from I to J, then you always have an arrow, the other arrow starting at I. And then you have a permutation G. Also a permutation of arrows. G of alpha is F alpha bar, and so you have alpha, and there is G alpha and F alpha. And so in this picture I have drawn G, so G is always then in the top one, sorry. G is always the going around the white triangles. And here G is more complicated. So if you have alpha, then G of alpha doesn't go around the shaded triangle, it goes the other one. And so G of beta, you can't go around the shaded triangle, you have to go here. And then, yes, then you'll be back to alpha, and then you can do that for each arrow, and you get cycles of different lengths. Okay. So you can also change the orientation in one of the triangles and produce double arrows, and then you get a different G and a different algebra. So there are lots of these algebras. So now we want an algebra to that. And so we have to take the path algebra and define relations. And I've written it down because it needs some notation here. So for each, okay, so what is the word itself is algebra. So you need, so we have this permutation G, and so we have the cycles of G, so alpha is the cycle. So you have the O alpha is the cycle of G, alpha. And so it has a length. In alpha. So in these examples it was what could be 1, 2, 4, then you have M alpha, which is the multiplicity. Then you need C alpha in K should be non-zero, and these should be constant on orbits. Alpha. And so with these data you can define relations. So you would want a symmetric algebra, so you would want relations which go almost to the bottom of the projective. So here's a picture of a projective module. So it has bases. The basis is being given in terms of G, and so the relations given by F, and so you have to go almost to the bottom but not quite, and so you have elements which are just products of alpha bar, G alpha, and so on. And you take it as much as you can in alpha bar minus 1, and then you have to take more. And then if you go one step further, you want to go to the get into the socle of the algebra, and this should also be the same as if you do that with alpha. And so you have elements in this algebra, in this path algebra, and relations. What you factor out is so alpha, here's alpha, and then you have F alpha. You want to go to a scalar multiple of this almost socle element, and this should be true for all arrows. And then you also want some zero relations because you want a finite dimensional algebra. So if you have alpha, F alpha, and then the other arrow from there would be G of F alpha, and this should be 0. And so this will be relations which look the same at each vertex, but of course you have some different scalars coming in and some different multiplicities, and so you get algebras here. And so the theorem is that any of these weighted surface algebra is actually of generalized quaternion type. So they have gone again. So the simple modules are periodic of period 4. It's tame and symmetric. And in fact, it is true as they are periodic as algebras. So in this case, one can actually compute projective resolutions. And so we're working on a possible converse, namely if you have a generalized quaternion type with two regular quiver, so you have two vertices, each vertex 2 arrows in and 2 arrows out, that this actually is weighted surface algebra. Actually, I've forgotten there's one exception, right, this exception. There is a singular tetrahedral algebra, so what is this one here? So the quiver is tetrahedral. This was my first example. Let me go back to that. So this top quiver is a tetrahedral quiver. And so then you have, for each vertex, you have a multiplicity. So the multiplicities should all be 1. And then you have a condition on the scalars, and the product of the scalars, if this is 1, then you do not have periodicity. This is not periodic, and it does not have not quaternion type. So in this case, the simple modules are not periodic. And this is the exception, and we're thinking about the converse. Right, so this is very good timing because it's all I wanted to say. Okay, thank you.
Questions?
Yes, I suppose it's lunchtime, right?
No, I think it's estimate the clarity of the lectures. Let's thank Karen again.